Dear students, in this class we are going to solve few numericals on heat exchangers. So let's begin with the first numerical. Just I am copy pasting it in PPT so that you will understand. So I am going sequentially. The questionnaire is already with you. I am solving numerical number 8. Let's paste it here so that we can interpret the data. Yeah, let's do it. Just I'm checking whether the recording is on or not. Okay, fine. So let's interpret the data from the given problem. Whenever you are seeing the problem of heat exchanger, it's very important to identify the type. Generally, the numericals in examinations are asked on parallel flow heat exchanger, counter flow heat exchanger, condenser or evaporator. When we are talking about condenser and evaporator, there is no question of parallel flow and counter flow. Means in condenser or evaporator, if you solve the problem by parallel flow or by consider it as a counter flow, the answers are going to remain same. Why? Because in condenser and evaporator, one of the fluid is always changing the phase. So there is no problem of parallel and counter. But if condenser and evaporator is not mentioned and only it is mentioned at parallel flow or counter flow, you need to draw the proper temperature profile. So that is very important step. So again recall, what is the first step in heat exchanger problem? Try to understand or identify what type of heat exchanger it is. Is it parallel flow? Is it counter flow? Or is it condenser? Or is it evaporator? Okay, condenser and evaporator falls in same category. ठीक. Now, the flow rates of hot and cold water streams running through a parallel flow. This is very important. So we had identified what is heat exchanger. It is parallel flow type. So let's draw the temperature profile structure for parallel flow. Just 1 minute. This is TH1. This is TH2. Hot fluid is exchanging heat means the temperature of hot fluid go on decreasing. TC1 and this one is TC2. Temperature of cold fluid is increasing. And see here why it is a parallel flow temperature profile, because both the fluids are having entry from left side and both the fluids are having exit from right side. So see the arrow direction, both are flowing in the same direction. So it is a temperature profile of parallel flow heat exchanger. So difference between TH1 and TC1 is theta1 and difference between TH2 and TC2 is theta2. Okay. Now just put down the data. Okay. जैसे ही आपने हीट एक्सचेंजर के टाइप को आइडेंटिफाई किया, आपको टेम्परेचर प्रोफाइल को ड्रॉ करना है. तो मैंने आइडेंटिफाई किया पैरेलल फ्लो and I have drawn the temperature profile diagram for parallel flow heat exchanger. Now you have to write the data by separating hot fluid and cold fluid in two different columns. So hot fluid and then cold fluid. Okay, and both fluids are water, hot and cold water. So both fluids are water. So on hot side also I will write water and on cold side also I will write water. Okay. Okay. Just 1 minute. There is an issue with internet. Now, the flow rates of hot and cold water streams running through a parallel flow heat exchanger are 0.2 kg per second and 0.5 kg per second. So hot m dot h, how to read it? M for mass, h for hot fluid, and dot for mass flow rate of hot fluid. So it is 0.2 kg per second, that is given. Okay, and m dot c is how much? It is given as 0.5 kg per second. Okay, so already it is in kg per second. If it is in kg per hour or kg per minute, you need to convert it in kg per second. Next, the inlet temperature of hot and cold side are 75. Inlet means what? 1, and outlet means 2. Hot means H and cold means C. The inlet temperature of hot and cold sides. So inlet means 1. So TH1 and TC1. This is 75 and this is 20 degrees Celsius. So TH1 is equal to 75 degrees Celsius. TC1 is equal to 20 degrees Celsius. The exit temperature of hot water is 45. So exit temperature of hot water, exit means 2 and hot means H. So TH2 is 45 degrees Celsius. So TH2 is equal to 45 degrees Celsius. If the individual heat transfer coefficient on both sides is 650, so H on hot side, so I will write H of hot side and H of cold side, it is 650, both they are same, watt per meter square Kelvin or degree Celsius, it doesn't matter. This is also 650 watt per meter square Kelvin. Calculate the area of the heat exchanger. So what is the required answer? The required answer is only one area of the heat exchanger is asked to calculate. Still there are some connectivity issues. Just 1 minute. I'm reconnecting it. Yeah. Okay. So the problem is all set. Now we will go for the solution. What is question? Area of the heat exchanger. Now let's go to the solution. Now I need to calculate area. So in which formula area lies? In heat exchanger, there are two approaches to solve the problem. The first approach is LMTD approach and the second approach is effectiveness NTU approach. When to use LMTD and when to use effectiveness NTU approach depends on if out of 4 temperatures, how 4? Hot fluid 2, entry and exit, cold fluid 2, entry and exit. Out of these 4 temperatures, if any 2 temperatures are known and 2 are unknown, if 2 temperatures are known and 2 are unknown, generally 2 means inlet temperatures are known and outlet temperatures are unknown. If such situation arises, we have to go for effectiveness NTU approach. And if 4 temperatures or 3 temperatures are known to us, again I repeat, if 4 or 3 temperatures are known to us, we need to go for LMTD approach, logarithmic mean temperature difference approach. So in this problem, out of 4 temperature, TH1 is known, TH2 is known, TC1 is known. Only TC2 is unknown. So out of 4, 3 are known. So we can use LMTD approach. Now you are saying, sir, whether these 2 approaches are alternative to each other? Yes, they are alternative to each other. But sometimes if the condition is not met, means if 2 temperatures are unknown out of 4, then we need to solve the problem only by effectiveness NTU method. You can't solve this problem by LMTD method. Because in LMTD method, you require all 4 temperatures or at least 3 minimum temperatures to be known. Then and then you can use the LMTD approach. But if all 4 temperatures are known to you and then it is asked by which approach you should go, you can use either LMTD approach or effectiveness NTU approach. By both the approaches, you will get the same answer. Okay, but for this problem, out of 4 temperature, 3 are known. So which condition is met? LMTD approach we can use. And out of these two, which one is the easier method? LMTD method is the easier method. So if there is a choice for you, by which way you should go, so I will suggest out of these two choose LMTD approach. Okay, but remember one thing, if 2 temperatures are unknown, you don't have a choice. Out of 4, if 2 temperatures are unknown, you don't have a choice. You have to go only for effectiveness NTU approach or method. You can't use LMTD method. This is very, very important. So let's start. So out of 4 here, 3 are known. I can use LMTD method. So let's do it. So by LMTD method, the basic formula is Q is equal to U A theta m UI means overall heat transfer coefficient based on inner area. Then of course inner area AI is coming and then theta m. If it is based on outer area, then UO, outer area AO and then theta m. And if radius, inner tube dimension and outer tube dimensions are not given, then you can use the general formula UA theta m. Okay, if inner radius is given, you can use this. If outer radius is given, you can use this. So dimensions are given for the tube, you can use this one or this one. If dimensions are not given, you have to use this formula. So this is very, very important. So in this formula, what is area? Area is equal to Q upon U into theta m. Theta m is LMTD. Okay, logarithmic mean temperature difference. So this is the basic formula to calculate the area. Okay, I will write this as equation 1. Okay, from this you will get area. So how to get the first Q? If you know Q, I must know this capital Q. If I want to know the area, I must know capital Q, overall heat transfer coefficient U and LMTD theta m. So let's do one by one. Q is equal to m dot h Cph Th1 minus Th2. This is the heat balance equation for hot fluid. Now energy equation for cold fluid is m dot C Cpc Tc2 minus Tc1. So this is the energy balance equation for heat exchanger. So let's put the values. Q is equal to m dot h. How much it is? 0.2. Cph. Specific heat of water is not mentioned. Remember students, if water is there, generally specific heat is not mentioned. So you must know its standard value. 4187 joule per kg Kelvin. What is the specific heat of water? 4187 joule per kg Kelvin and 4.187 kilojoule per kg Kelvin. So you are saying, sir, whether to substitute in joule per kg Kelvin or kilojoule per kg Kelvin. If you want the answer of Q in watt, you must substitute the value in joule per kg Kelvin, not in kilojoule. So it has to be 4187. Then TH1, what is TH1? 75. What is TH2? 45. 75 minus 45 is equal to m dot C. What is m dot C? 0.5 kg per second into Cpc. I think both hot and cold water means hot fluid is also water and cold fluid is also water. So again 4187. Tc2 unknown, that is not known to you. Tc2 unknown minus Tc1. What is Tc1? 20. Okay, I will solve this first. So what is the answer of Q? The Q comes around 25.12 into 10 raised to 3 watt. This is the value of Q, and I will equate this with this. So 25.12 into 10 raised to 3 is equal to 0.5 into 4187 into TC2 minus 20. If I will do the calculation, TC2 comes as 31.99 degrees Celsius. 31.99 degrees Celsius. Okay, that is TC2. Now you are knowing all four temperatures. TC2 also I am putting on the temperature profile. You are knowing all four temperatures, so you can proceed to calculate theta m. Okay, but we will go sequentially. I know now Q. This is 25.12. Now next job is to calculate U. Okay, look at the problem. In this problem, nothing is mentioned about the tube dimension. Heat exchanger dimensions are not given. Inner radius, outer radius of the tube not mentioned. So in this case, how to calculate U? So as this is the first problem, I am writing the formula. If the dimensions of heat exchangers, if the dimensions of heat exchanger tube, heat exchanger tube are not given, then 1 upon U is equal to 1 upon HI plus 1 upon HO. Now what is HI? Heat transfer coefficient on inner side. And what is HO? Heat transfer coefficient on outside of the tube. HI means inside the tube, on inner surface of the tube, and HO means from outside the tube. So in this case, nothing is mentioned what is inner and what is outer. Okay, whether which fluid is flowing from inside and outside. So in this case, HI and HO separation is not there. So anything you can take. It is commonly given as 650. Both side it given as 650. So 1 by 650 plus 1 by 650. If I will calculate from this, the value of U comes around. The value of U comes around 325 watt per meter square Kelvin. So I got the value of U. This formula is, remember, this formula is used, I am highlighting this. Remember, this formula is used only when above condition is met. What is the above condition? If the dimensions of the heat exchangers are not given, means inner tube radius, outer radius, or inner tube diameter, outer tube diameter, such things are not mentioned, then and then this formula is used. Otherwise, we need to go for different approach to calculate U. So this is very important in this problem. So U I got, and now the last one is remaining, that is theta m. So for theta m, you require theta 1. What is theta 1? Theta 1 is theta 1, that is TH1 minus TC1. TH1 minus TC1. Theta 2. TH2 माइनस ये TH2 है और ये है TC2. सो दोनों का डिफरेंस TH2 minus TC2. So TH1 minus TC1. So that is the benefit of writing the values on the diagram. So directly you can pick the values from there. TH1 minus TC1 is 75 minus 20. You look at here, 75 minus 20. And TH2 minus TC2, 45 minus 31.99. 45 minus 31.99 is equal to, what is the value of theta 1? Theta 1 comes around 13.01 degrees Celsius, and theta 2 comes around 55 sorry, something. Theta 1 comes around, wait a minute, it is something. Theta 1 comes around 55 and theta 2 comes around 13.01 degrees Celsius. So what is LMTD? Theta m, it is theta 2 minus theta 1 divided by natural log of theta 2 by theta 1. So if I will put the values, 13.01 minus 55 divided by natural log of 13.01 divided by 55. If you solve this equation, it comes around, the answers of theta m, that is the LMTD, comes around 29.12 degrees Celsius. Okay. Now you know everything. So by equation 1, by equation 1, we get A is equal to Q upon U theta m. What is the value of Q? 25.12 into 10 raised to minus 3. 25.12 into 10 raised to not minus 3, it is plus 3, divided by U 325 into theta m is 29.12, and that answer is coming as 2.6542 meter square. So this is answer. Okay, only one is asked, so this is the answer. Okay, so by this way you have to solve the problem of heat exchanger. So it's a very starting problem. Okay, just give me a minute. I will save this file somewhere and reopen it so that this connectivity issue is there, that will get solved. So let's begin with the next problem. Number 9. Start interpreting the data. Now I am reading the statement of the problem and writing the data. The flow rates. What is the first job? To identify the type of heat exchangers. Just read the statement. Flow rates of hot and cold water streams running through a counter flow heat exchanger. So the type is counter flow. Okay, counter flow. So draw the temperature profile diagram for counter flow. So what is counter flow? For example, hot fluid is making entry from left side and making exit from right side. So this is TH1 and TH2. But now cold fluid is making entry from opposite side. So it has to be from here. And then the cold fluid temperature go on increasing. So this is your TC1 and this is your TC2. इन दोनों का टेम्परेचर डिफरेंस क्या होगा? थीटा 1 एंड इन दोनों का टेम्परेचर डिफरेंस क्या होगा? थीटा 2. ओके, ठीक है. सो you have drawn the temperature profile diagram for counter flow and put the values of theta 1 and theta 2. ठीक. Now you have to make two columns, as I said. in first problem. What fluid column and then cold fluid column. Both hot and cold water. So both are water. Both fluids are water. So their specific heat is known to us, that is standard value 4.187 kilojoule per kg Kelvin, but you are not substituting kilojoule, you have to take it as 4187 joule per kg Kelvin. Then their heat flow rate are mass flow rates are for hot fluid is, so m dot h is 0.2 kg per second, m dot c as 0.5 kg per second. Next, the inlet temperature on hot and cold sides are 75. So inlet temperature of hot fluid 75, inlet temperature of cold fluid 20. Now you are saying, sir, this problem seems to be last problem. Yes, all the values are same. Only difference is parallel flow is there in last problem and here it is a counter flow. Everything, all data is same. Only what they have changed, instead of parallel flow, they have made a counter flow arrangement. So m dot h and m dot c. Next, th1 is given as 75 degrees Celsius and tc1 is given as 20 degrees Celsius. tc1, okay. The exit temperature of hot water is 45. So th2 is 45. I am writing at both places, in data table also and in figure also 45. Why I am writing in figure? The reason is I can pick the values from there while calculating theta1 and theta2. So that will be easy for me. Next, if the individual heat transfer coefficient on both sides, so h of hot side is equal to h of cold side, because individual heat transfer coefficient on both side means hot side as well as cold side, that is hot fluid side and cold fluid side is same. So h of hot is equal to h of cold is 650 watt per meter square degree Celsius. And what is asked to you? Required answer is area of the heat exchanger. So just like previous problem, you have to solve the problem. Okay, just like previous problem. So then you are saying, sir, whether the answer is going to be same because all the data is same? No, answer is not going to be same. What is the reason behind it? There is a reason key LMTD of parallel flow heat exchanger and LMTD of counter flow heat exchangers are going to be different. Now how they are different? The reason is they are traveling in opposite direction. In parallel flow, they are traveling in the same direction. Therefore, theta1 and theta2 values are different. As theta1 and theta2 are different, LMTD theta m is also different. And if theta m is different, naturally your area is going to be different. And that's why we need to calculate the area for counter flow arrangement again, and definitely you will find the area answer is different from previous problem, though data is same. So let's start the solution. What is Q? Q is UA theta m. Okay, this is the fundamental equation. Or UI AI theta m or UO AO theta m. This is used only when the dimensions are given, and this is used when dimensions are not given. So in the problem statement, dimensions of the heat exchanger tube is not given, so I will use this formula for calculation of area. So what area is? A is equal to Q upon U theta m. So to calculate area, I require Q, I require U, I require theta m. Q is heat transfer rate, U is overall heat transfer coefficient, theta m is LMTD. So let's start with first calculation of Q. By energy balance equation, Q is m dot h Cph Th1 minus Th2 m dot c Cpc Tc2 minus Tc1. So let's start Q. M dot h. What is m dot h? 0.2. Okay. Hot and cold side means both the side there is a water. So what is the water specific heat? Joule, 4187 into Th1 minus Th2. Th1 कितना है 75, Th2 कितना है 45. 75 minus 45. If I will calculate this, I will get the answer of Q as, just 1 minute, 25.12 into 10 raised to 3 watt. Okay, I got it. Now the next target, I need to get U. So in last problem I already told, if the dimensions of the heat exchanger tubes are not given, the overall heat transfer coefficient is calculated by the formula 1 by U upon 1 by HI plus 1 by HO. What is the meaning of HI? Heat transfer coefficient on inside, and HO means heat transfer coefficient on outside. Here they have not differentiated between inside and outside, they have given only on hot side and cold side, and nothing is mentioned which fluid is flowing inside or outside. So you can take anything for HI and anything for HO because both are same. So HI is how much? 1 upon 650 plus 1 upon 650. If I will calculate this, the answer of U is coming as 325 watt per meter square, degree Celsius or Kelvin. You can write anything. Now I got Q, I got U. Now theta M. For theta M, I require theta 1 and theta 2. So what is theta 1? Theta 1 means temperature difference at entry. What is that? TH1 minus TC2. Counter flow है TH1 minus TC2. TH1 minus TC2. And what is theta 2? TH2 minus TC1. TH2 minus TC1. This is theta 2. Okay. Now is equal to TH1 minus TC2. TH1 is 75, but TC2 I don't have, and that is the problem. I think we haven't obtained it. Just wait here. I will come to theta 1 and theta 2 later. First we need to know about TC2 because only 3 temperatures are known. Okay, from 3 temperature we need to find out 4th unknown. How to do it? See here, you know Q value. This I can equate with this because energy balance equation states that. Okay, but you know Q value. So Q is what? 25.12 into 10 raised to 3 is equal to m dot C. What is m dot C? Look at here, 0.5. What is specific heat of water? 4187 into what is TC2, that is unknown, and what is TC1? TC1 is given as 20 degree Celsius. यहाँ आपने put किया है 20. So if you solve this, the answer of TC2 comes as, just 1 minute, I have already done it. TC2 comes as 31.99 degree Celsius. Okay. So now I will again revisit to calculate. Now all 4 temperatures are known. So you can calculate theta 1 and theta 2. What is theta 1? TH1 minus TC2. And what is theta 2? TH2 minus TC1. So TH1 and TC2. This TC2 I will put on the diagram. TC2 is what? 31.99. Okay. So what is theta 1? 75 minus 31.99. And what is theta 2? 45 minus 20. So this is the benefit of writing all the values on the diagram. So theta 1 and theta 2 can be easily calculated. So 75.39. So 75 minus 31.99, it comes around 43.01 degree Celsius. And 45 minus 20 comes around 25 degrees Celsius. So how to calculate LMTD from theta 1 and theta 2? Theta 2 minus theta 1 divided by natural log of theta 2 by theta 1. It seems LMTD formula is same, but the answer of theta 1 and theta 2 for parallel and counter flow are different, and therefore LMTD answer is also different. So what is theta 2? 25 minus 43.01 divided by natural log of 25 upon 43.01. So if I will calculate it, the answer of this is coming as 33.19 degrees Celsius. So therefore, if I want to calculate area, area is equal to, what is Q? Q is 25.12 into 10 raised to 3. What is U? 325 overall heat transfer coefficient, that is calculated here. And what is theta m for counterflow? 33.19. If I will calculate this, the answer is coming around 2.3278 meter square. So this is the answer. Now student, in last problem, same data is there, and that was parallel flow heat exchanger. And this problem, same data is there, but the problem is for counterflow. Let's compare the values. Now, what is the LMTD value for parallel flow heat exchanger? It is 29.12. Let's assume 29. And what is LMTD value for counterflow? It is 33. So there is 29 and here is 33. So LMTD value is different. Same data, but for parallel flow and counterflow, LMTD is different. LMTD for counterflow heat exchanger is always higher side, and therefore you will find area of counterflow heat exchanger is always less than parallel flow heat exchanger. You can check. What is the answer in parallel flow? 2.6542. 2.65, let's say. And here, what is the answer? 2.32. So you see here, for the same heat transfer, if I am using a parallel flow heat exchanger and if I am using a counterflow heat exchanger, which one is beneficial? Naturally, counterflow heat exchanger is beneficial. Why? Because in this case, see, in last problem, how much heat we need to transfer? 25.12 into 10 raised to 3 watt. In this case, is in counterflow heat exchanger is also, it is same heat. But to transfer this same heat, area for counterflow heat exchanger is 2.32 meter square. Whereas in parallel flow heat exchanger, it is 2.65 meter square. So definitely counterflow heat exchangers are beneficial as compared to parallel flow heat exchanger in the industry. Okay, so that's it for today's lecture. As it's a preliminary class, we have solved basic numericals of heat exchanger. So only 2 numericals in this class. In next lecture, we'll go for some more numericals from heat exchanger. Thank you.